ever since then, yeah, I used to travel a lot. We all used to travel a lot. Right now, we're just getting used to our cats and dogs and families and stuff like that. But I was out just last week, and I set up the scope that you saw up in Colorado. It's a pretty nice mead. And I was noticing that the light pollution really, really, really stinks in Phoenix. It's really, really, really bad. No deep sky stuff, but you can still see stars and planets real nicely, even those of us who live in cities. So first and foremost, what would you say to people in our audience? Because I get this all the time. People sort of look at me and they go, "Oh, you're getting up at 2:00 in the morning to see Jupiter? That seems really silly." They live in cities. They've never seen what's up there. I mean, once in a while on a clear night, they see a few. They see Sirius up there. It's if I'm recalling correctly, the brightest star up there. But they just don't see what's up there. What do you say to folks like that?
Oh, you're depriving yourself of one of the most wonderful natural resources the Lord has given us. And the Bible singles out the heavens as declaring the glory of God. I mean, everything God made declares His glory, but there's something really special about the heavens, and you need to do that at least once in your life. And once you do it once, you might want to do it again because it's really spectacular. I found a spot again, hour and a half drive from here, where it's a zero light pollution, zero. And it is absolutely spectacular. Once your eyes get good and dark adapted, it's amazing. And I now have night vision, very high quality night vision goggles with white phosphor, and that's fun too because you look up and you just see all kinds of things that some stuff that I'd never seen before. Because for one thing, I have an H alpha filter for these night vision goggles, and that brings out certain nebulae. H alpha is a specific color of red, and a lot of nebulae have that specific color. The eyes don't pick up red well at night, but the night vision goggles excel at it. And so some things that I had never seen before, I was able to see just last year for the first time. And so it's kind of a new level of excitement for me. But yeah, you need to do that at least once. You need to get out to dark skies, preferably get access to a telescope and maybe somebody who knows where the good stuff is. And check it out. And of course, I do have a book that shows where all these cool things are at, The Stargazer's Guide to the Night Sky. If people get interested in that, they can get that on our website.
Well, now, you mentioned in a text, you said something about these night vision goggles. Now, are you talking about just having them on or using them to look through a scope? How does that work?
Yeah, both. The goggles themselves, I got them at zero magnification. So all it does, it doesn't make the sky look bigger. It just makes it 3,000 times brighter. And boy, does it look spectacular. And so just panning around is awesome.
Wow.
Then I can slap an H alpha filter on it, and all of a sudden, just you can see nebulae just in the sky. I built an adapter for it though, so I can stick it into my telescope as well. And boy, is that amazing!
Well,
so,
of course you built an adapter for it. You're Jason Lyle.
There are other ways to do it, but they require replacing the lens. I didn't want to do that, so I built a little adapter. It works really well, and you just slap it on there and stick it in, and boy, you should see the Swan Nebula with the H alpha filter. It's amazing. And so when you're here next time, if the situation allows for it, we'll have to. You'll get
well. But so now, so what you're saying is you can actually see nebulae, I guess the plural, without using the scope, just because you can't see them normally because of the faintness or just what.
And the color. There are a lot of really spectacular nebula. Some of them are bluish, and those you can see in a telescope and they look good.
Right.
The Dumbbell Nebula, the Ring Nebula. But then there's some that I've tried to look at in a telescope, like the North American Nebula. It's a big nebula, and it's red. And so even with the telescope, when you're using your night vision, the rods are peaked to the green, and they don't see red very well.
Right.
And so I've never really had a good view of the North American nebula until I got these night vision goggles, put on the H alpha filter, and you look without a telescope, you can look up, there it is, and it's just obvious, and it looks like North America. It's really amazing.
Really?
So, yeah, it's really spectacular, and,
Wow.
and some other ones too. The Lagoon and the Trifid, they just pop out, and the Lagoon is incredibly bright in H alpha. It's astonishing. The Eagle Nebula, which looks pathetic in a telescope even, but you put the H alpha filter on, and it's glorious. It's really amazing. So it's changed. It's pretty neat because they're things that I had not really seen before. I knew of them because I've seen these wonderful Hubble pictures, and I've tried to look at them, and maybe you can see them a little bit. They just pop out with the H alpha filter and the night vision goggles.
Wow, that's pretty cool. Now that filter, is that similar to, because I have some filters that I use to look at nebula, like when I look at Orion or something like that, and it does make it glow a whole lot more. Is that the similar type of concept?
Yeah, normally the ones that you would use if you just for naked eye viewing, or for viewing through your telescope without night vision goggles, the ones you'd probably get would be an H beta filter, which peaks in the green, and another one, oxygen 3.
Oxygen 3,
filter.
yeah, that's what it is.
Yeah.
That's what it is, right?
And those are great. But you wouldn't normally get an H alpha filter because that filters everything except a deep red that your rods can barely see at all. But but for the night vision goggles, they pick out red very well, and infrared even, they can see into the infrared a little bit.
Wow.
So normally you wouldn't get an H alpha filter just for eye viewing, but with the night vision goggles, it makes an enormous difference.
Okay,
it's really quite spectacular.
So now you're talking about infrared stuff. It's been about 20 years ago now that people started using infrared to probe into the center of our galaxy, because there's too much dust between us and the center of the galaxy to really be able to see a whole lot in that area.
Right.
But
Right.
I guess infrared allows you to get through that, and so that's how they've done the tracking of stars to be able to verify the existence of Sagittarius A star. Tell us a little something about what that's all about.
Yeah, we've suspected for a long time that there was a giant black hole in the middle of our own galaxy, but it wasn't until we started looking at the center of our galaxy. Sagittarius A is kind of the area that is the center of our galaxy, and A star is the exact location of this black hole. We've confirmed it now. And the amazing thing is we've actually been able to see stars orbit that black hole.
Right.
We've been able to track their motion for the last decade or so. And I even have one of the programs I have on my computer. It actually has those stars in their proper orbits, and you can speed it up, time lapse, and you can watch them orbit this black hole. It's astonishing. And within the last few weeks, even there was a new paper published where one of the innermost stars that's orbiting around there, they've been able to detect precession, which is where the orbits are elliptical, and their farthest point from the star. If Newton's laws were exactly right, that would never change. The longest point in the orbit would stay in the same location. But because of the physics that Einstein discovered, orbits precess. The ellipse actually itself rotates, so it makes a spirograph pattern if you watch it over time. And they've been able to confirm that within the last few weeks that this inner star has precessed in accordance with the equations that Einstein discovered. So it's a remarkable confirmation of general relativity, and it's just interesting physics. Black holes are awesome, and I have a whole chapter on them, or maybe 2 chapters on them in the book that I wrote on the physics of Einstein, because they're just neat, and it's neat to see confirmation that we do have one in our own galaxy. We actually think that pretty much all galaxies have a giant black hole in their center.
Yeah, so don't you think using the Men in Black universe, don't you think Einstein was clearly an alien? I mean, because he was so bright, and he didn't have any of the stuff we've got today, and yet we keep proving him right. So I mean, he clearly was from another galaxy, don't you think?
I would actually put Newton in that bin, because Newton, of course, Newton didn't have the benefit. He's centuries earlier, and he didn't have the benefit of the many things that we know today.
Right.
But Newton discovered more things than any one person has any right to. Any one of them would be Nobel Prize worthy today. I mean, he discovers the nature, the formula for gravity. He discovers that planets orbit the sun because of gravity. The math didn't exist at the time, so he discovers the math, calculus, that allows him to demonstrate that. He discovers basically everything we know about optics. Newton figured that out. Just an incredible mind. Einstein made one very brilliant creative leap, and that is that lengths and the measure of time are not universal. That is, depending on how you're moving, you will experience time and lengths differently from someone who's moving differently. Once you realize that, and you incorporate the fact that the speed of light, the round trip speed of light, is constant with any observer, the rest of relativity follows naturally from that. You can derive it all mathematically, and I demonstrate in my book, The Physics of Einstein. I show that algebraically you can derive all the rest of relativity just from that one amazing visionary. So Einstein, he got one thing incredibly right, and it was ingenious. But it was Newton that kind of made all these different discoveries, and you're like,
Right.
How did he do that?
I have no idea. Well, sometimes, honestly, I wonder if back then, without the number of distractions.
There's that.
Now, going back to the center of our galaxy for a moment, I watched a documentary type thing about the discovery of all this stuff, and one of the things you were just talking about, the orbit of these stars, this massive black hole is able to take huge stars and whip them around at incredible velocities.
Mm-hmm.
I mean, the power is difficult for our little minds to even begin to imagine.
Mm-hmm. Oh yeah, it's awesome. It's awesome. And the weird physics kicks in when stars get really close to the black hole. If you're far away from a black hole, physics works kind of normal. It's
Right.
things, people have, I've asked this question to folks. I said, what would happen if I took the sun and compressed it into a black hole? And people think, the Earth would just get sucked into it. No, the Earth would continue to orbit just as it does right now. There's nothing weird about that. You can orbit around a black hole until you get really close. And then once you get really close to it, the physics gets a little bit wonky. The physics differs from the expectations of Newton's
Right.
physics. Newton's physics you can think of as an approximation that works very well if gravitational fields are relatively weak and if the speeds are relatively slow compared to the speed of light. But if speeds get close to the speed of light, or if the gravity gets very, very intense, as it does near a black hole, you can't rely on the physics of Newton. You have to use the better approximation, the physics that Einstein discovered. And you say, well, why even keep the physics of Newton? Because it's much easier. And so, much easier. And so, if you can get away with using the Newton approximation, you should, because it's far easier to work the math that way. The physics of Einstein gets into some very difficult mathematics.
So, okay, I wasn't going to ask this, but what did you think about the movie? Oh, good grief! It just flew out of my mind. A couple years ago with the black hole.
Interstellar?
Yes, Interstellar. Yes.
All right. I enjoyed it. The ending I thought was wonky. I didn't like the ending, but the rest of it was intriguing, and it was one of the most realistic depictions of a wormhole I've ever seen. And that's because they consulted Kip Thorne, who is one of the world's PhD in physics, expert on black holes and wormholes. They consulted him to get that right. They took some license, but you expect that. I mean,
Right.
if I can enjoy Star Trek, I can appreciate taking license from science.
That's right.
But the planet that they landed on that's very close to a black hole and therefore experienced extreme time dilation, that was really neat. The amount was off. Gravitational time dilation is normally very, very small, and the energy required to leave a gravitational well where the time is that slow, it's not realistic. But nonetheless, it was a really cool concept, and it's true in principle that when you something orbiting close to a black hole, time slows down, and
Wow.
you don't realize it because everything slows down together. Your brain slows down, your watch slows down, and so it looks normal. But then when you come back out, you realize the rest of the universe has aged 20 years, and what has been a month or so for you. And that's real physics, and we can demonstrate that happens. We've been able to measure it using atomic clock. We can't get very high speeds or very intense gravitational fields, but even in the weak gravitational field of Earth, we can measure gravitational time dilation using atomic clocks, and it's true. And
Yeah.
it's exactly what Einstein predicted. So it was a fun movie, and The ending was a little strange, but other than that, it was pretty good.
Well, you're actually right near one of the main atomic clocks.
Yeah.
There in.
I used to be much closer because it's actually up in Boulder, is where they have the atomic clock, one of the atomic clocks that is
Right.
used.
Right.
And the transmitters in Fort Collins. I still have a clock over here that I use that gets the signal from the Fort Collins.
Right.
The radio transmission from Fort Collins resets itself to the atomic clock every night, so I never have to set it. It's exactly right. That's kind of neat.
It is. It is.
Useful in astronomy.
I remember. Hey, you'll be proud of me, but I was. Oh goodness. I think I was a teenager, maybe, when my dad told me about that stuff, and you could string up an antenna, and you could actually listen to that thing. I mean, it's as boring as all get out, but you could listen to that tick tick tick, and then and you get your exact time settings from stuff like that. So that was long before any of the watches and all the rest of the stuff that you've got today that you can do all that fun stuff.
Yeah,
with.
even when I was in grad school, they didn't have. I don't think they had the clocks, or if they were, they were rare.
Yeah.
But it was a local phone call, so you could call it. It's kind of neat, and listen to the signal there and set your watch by it. So it's kind of neat.
And I'm sure there were a bunch of you guys there in Boulder who were complete nerds and geeks that were calling that number fairly regularly to make sure that your watches were spot on. That's right. We know who you all were. We suffered through your blowing the curve on every test and everything else. We've been there, done that, got the T-shirt. You said, hey, on Saturday we get done at like 3:00 in the afternoon. How would you like to go stargazing? Now, I had never done that. I had wanted to. I had looked at telescopes. I had an interest in these things. I had a science background, science major, but it was biology primarily. But I was still interested in those things. And anybody who does a degree in physics is just really weird. Let me just mention that in passing. So we went out. You set up your 16-inch Dobsonian out there actually it was right next to a road, which was the best we could do, I suppose. But there were a few times. In fact, didn't a cop come by once? Am I remembering that correctly?
He said we could set up there, but I couldn't park my car where it was. So
that's right.
Yeah.
That's right. Anyway, so we went out there, and it'd been a long day. We were a little tired, and I've noticed that you have a hierarchy of celestial stuff to show people. You know what's up there, and you put it in order, so you don't start with all the cool stuff up front necessarily, and then people get bored as they go along. You wait till to throw them some good stuff. And you were doing that in Colorado last year because I had focused in on Saturn before you did. You were holding that one off to a little bit later on. So
you got to save Saturn. There's nothing better than that.
Oh no, there isn't. It's glorious. I think Jupiter and its moons are pretty cool. And of course, when you did show us Saturn, you start whipping off all the names of the moons and all the rest of this stuff. I had no idea about a lot of that stuff. I've done a lot of reading on it since then, and some of just the moons of the gas giants are fascinating in and of themselves. They really, really are. But one of the last things you did, now you had mentioned being able to see galaxies. And so I had asked, I'd really like to see a galaxy, And so you moved over to the Andromeda galaxy. And that's the first time I'd seen anything like that. And so I'm like, okay, now that's pretty cool. And the interesting thing is, and I bet you can you see that clearly with the night vision goggles?
Oh yeah,
I bet.
No problem.
Because I finally saw it without a scope or binoculars, with my not so good eyes, up there in Flagstaff at 8,000 feet in total darkness. And then it was like, how can I miss that? I mean, it's right there.
It's the farthest thing that is detectable to the unaided human eye.
Is the Andromeda galaxy.
Yeah.
So all the other galaxies would not be visible.
Right. There's two in the southern hemisphere, the Magellanic Clouds, that are visible to the unaided eye, but they're closer than Andromeda. So it's the most distant object visible to the unaided eye.
Okay. All right. Well, and so it must be pretty pretty bright to be that far away, and yet we're able to see it with the unaided eye in total darkness. So I was pretty amazed by that. And then, of course, you did Saturn, and yeah, that's beautiful, and all the rest of that stuff. But that's not what got me. None of that was what got me. Do you remember what got me?
Albireo.
Albireo, yeah. Which is I think it was one of the very last things that you showed us, was Albireo. And when I walked up to that scope, and if people don't know, a 16-inch Dobsonian is, how long is that thing? Is it about
6 feet.
Yeah.
And it's actually a 14-inch.
Oh, 14. Oh, I thought it was 16-inch. Okay, all right. I was giving you a little extra there, pumping up the stats or whatever. So
there is a 16-inch version, but the base plate goes from 60 pounds to 90 pounds. It gets really heavy.
Well,
really fast,
I was stunned. Your car is not big. I don't know how you got all that in there.
But it's a Camry. It's got a big trunk, so that helps.
Still, yeah. I was just amazed at how you were able to pack that all in there. I'm sure you have a computer program that you designed and wrote yourself that told you how to do that. But anyway, yeah, I walk up to that thing and I can still remember. I look through the eyepiece and here is this glorious gold star, and right next to it, this glorious blue star. And it did. I don't know that it struck me that night, but it has certainly struck me since then. I've looked at a lot of doubles through my scopes. I've never seen a double that can compare to Albireo. I just can't. The color contrast is stunningly striking. It really is. And then the thought that crossed my mind always is, who was the first person to realize that was a double star? Because you can't resolve it with the naked eye.
Right.
So all of the great men of the past had looked up, and if they had seen Albireo, which is not the brightest star in the sky, if they had seen it, they thought they were simply looking at a single star, not realizing that they were in fact looking at a beautiful double, and in fact it may be more than that. My reading has told me it's about 450 million light years away. Is that approximately?
No, 415 light years.
Okay, 415 light years. That's right, not million, but it's 415 light years. So it's sort of in our neighborhood, I guess you would say. But one of the things that you said that night that I remembered was, we're not sure it's a true binary. So what is tell us a little bit about it.
Yeah, so it's a double star. Anything is a double star if you see two stars close together. It's a double star. But the question is, do those stars orbit around each other?
Right.
Are they a binary? And that's been an ongoing debate for the last 20 years. Possibly settled just this past year. We think it's probably not a true binary, which is a little disappointing to me.
But it is to me too.
Yeah, but it's now it's now my favorite double star, but it's no longer my favorite binary because it's not a binary. That honor now goes to Almac, which is the winter version of Albireo. It's not quite as good as Albireo, but it's pretty nice. Almac.
It is.
But anyway, yeah. So in how do you determine that? Well, one thing is the two stars. If it's true binary, the two stars will be at about the same distance. In a lot of optical doubles, one star is much closer to than the other. They just happen to be lined up. And so if you get two different distance estimates, they're just two stars that are by coincidence are close together in that part of the sky as viewed from Earth. From a different location, they'd look far apart. Now it turns out these two stars are at about the same distance, so they could be a binary. The Hipparchus mission, which measured distances and locations of stars, measured the blue star to be slightly closer to us, but it was within the error bars of the two measurements. They could have been binary. More lately, we've had the Gaia mission, which is another mission to measure the positions and distances of stars very precisely. And Gaia also puts the blue star a little bit closer than the gold one, but again within the error bars. But the thing that makes it pretty clear that it's not a true binary is the proper motions of these stars. Proper motion refers to the motion of a star along the sky from our perspective on Earth, as opposed to a radial motion toward or away from the Earth. And the Gaia mission measures that. And if the measurements are right, these two stars are moving in very different directions to the point that it would be far greater than their escape velocity, which means they're not gravitationally bound. So if that data is right, Albireo is not a true binary. In terms of the blue and the gold, they're not gravitationally bound to each other. However, the gold star is itself a binary, and there's no doubt about that. It's orbited by at least one and possibly two stars that are very close. You can't split them in a backyard telescope, but professional observatories have been able to detect a very close companion to Albireo A. So it'd be Albireo Albireo AB is what it would be, and Albireo AC. So the gold star it was three stars. And the blue one is just one that it's photobombing the group. It just happens to be in the way.
It's photobombing.
Yeah.
So how long do we have to look at Albireo before it separates and you can tell it's two different stars?
You're not going to have to worry about it. Let's put it that way. It's going to be
Oh, wait a minute. Are you saying I specifically don't have to worry about it, but
anyone
my kids
listening
might?
to this podcast is not going to have to worry about it. You're going to have Albireo for your lifetime. Even if they extend our life by a factor of 10 through some kind of achievement, you're still going to have Albireo. The motion is very, very small. It's not noticeable within many human lifetimes.
Okay, all right. You had me worried there for a second, because the first thing I did when I got back from Dallas is I decided, okay, I'm not going to get some big fancy thing that I don't end up using. Telescopes are not all that expensive, amazingly.
No,
I mean, ones that
really.
can actually work well. So I got a little 6-inch Dobsonian, and I'm like, okay, let's make sure we're going to use this. And the first thing I did was searching for Albireo, and I remember the first time that thing showed up, I'm like, yes, there it is. I wasn't dreaming it out there, and so I would highly recommend anyone who is going to be getting into all this. That's something you're going to want to be looking at early on. Showing the kids. I know I showed my grandkids that up in Vegas, but now they live here in Phoenix, and so I need to drag them out to a nice dark spot and give them another sky tour, because that's a whole lot of fun. Now, I think I might have something that you don't. I have a solar scope. Do you have a solar scope?
Not a good one. No.
Not a good one?
No.
I'm not sure how you would define good one.
Well, I have solar filters that I can put on my binoculars, and they work superbly. I don't really have a good solar scope. When I was at the University of Colorado in Boulder, we had a wonderful, wonderful solar scope up there that I would use all the time, and it was just a blast. It was really well designed. It had a spectroscope built into it, and you look at the sun in multiple wavelengths. Right. It was a gem. And at some point, I want to build my own.
Of course,
of course,
neat. Yeah, of course. That's Jason Lyle. He's going to build his own. But yeah, no, mine's one of the the standard ones it's built specifically just to look at the sun, and you can see the surface, stuff like that. Of course, I bought it right as the minimum started. So I really haven't gotten much to see because this has been a really deep minimum.
It has.
It's been amazing. And my understanding is the depth of this minimum has impacted satellites and all sorts of stuff on Earth. Now, the sun is your baby, because if my memory's serving me correctly, that was what your dissertation was in. Am I correct?
Right. Yeah. Yeah. Solar photosphere, motions on the solar photosphere. Yeah.
Yeah. So tell us a little bit about when you and I are talking about a minimum, what are we talking about?
Yeah. So the sun goes through a 22-year cycle where the magnetic field flips every 11 years, and then it flips back. So the whole cycle is 22 years. And the sunspots correlate with that. Sunspots, during a certain point in that cycle, you have a lot of sunspots on the sun. And then at the other point in the cycle, you have very, very few, if any. And so every 11 years, you get a boost in sunspots. And that's part of that magnetic reversal. The sunspots are controlled by magnetism, if you're wondering what the connection is there. The sun's magnetic field is really interesting. It's different from Earth's. We have the and south pole. You have a simple, let's call it dipole magnetic field, north pole, south pole. The sun has that, and it has what we call a poloidal, or a toroidal field, where it wraps around east-west. And they're like two belts, one in the northern hemisphere, one in the southern hemisphere, at least two belts. And the sunspots almost always occur at the latitudes of those two magnetic belts. And so you'll notice when you look at images of the sunspots are not randomly distributed across the surface. They form two rows, one in the northern hemisphere, one in the southern hemisphere. And that's where those two magnetic belts are. A little piece of magnetism will pop up from that belt into the surface, and the two sunspots will form. Sunspots usually form in east-west pairs, and they have opposite magnetic fields because the magnetic field's going up one and down the other. So there's little pale pairs, really kind of amazing. And those belts move over the course of 11 years. They move toward the equator, and then they kind of cancel out when they get around the equator, and then you have very few sunspots. And the field flips then, and then you start a new cycle. A new belt forms at high latitudes, and then it's every 11 years, like clockwork.
Wow.
But some years are better than others.
Yeah.
Some years you get a solar maximum, you have lots of sunspots. Other years you have a solar maximum, you have relatively few. And there was a period of time, I believe in the late 1600s, early 1700s, somewhere around there, where you had the Maunder minimum, where you had very few sunspots. And it correlated with cooler temperatures as measured in Europe. And so sunspots do have an effect on Earth weather, far more than anything human beings have done, by the way. Far more.
Yes, I'm well aware of that. We can print all the funny money in the world, and it won't have as much effect as that big burning fusion engine in the sky is going to have. No two ways about it.